So, the next is contact resistance. So, in this contact resistance, basically we talk about two types of resistance. One is the streamline resistance. So, what happens in a streamline resistance? When you overlap two conductors and join it together, either through welding means or through using nuts and bolts. So, when you join this, now current is flowing like this. Now, this current has to come to this surface. So, now this will come like this and go like this. So, there is a distortion of current path here. If this overlap is very small, if this overlap is very small, what happens? The flow path, the current flow lines are not properly aligned. So, in such cases your resistance can increase. So, what the simple solution for such problems is that you increase the overlap portion, you increase the sufficient, whenever you are joining, you should have sufficient overlap between the two conductors. When you have this one, then the distortion of the current flow lines would be minimum. There would be distortion, but that would not impact anything much on the resistance side. And also it has to be uniform. The second thing comes because the contact resistance comes when you are having overlap of two surfaces. So, it is not 100% in contact. So, there is a microscopic region, there you have crest and other things something. So, you have both, only the point contact would be there. In such cases you have only point contact. However, you do not have a surface contact. So, when you have point contact, so your surface area of contact is very minimal. So, you need to reduce this point, you have to increase this point contact toward the surface contact. So, how can you do that? By, if it is a nut and bolted joint, then you have to increase the pressure by more tightening. So, in that case the more point, now you have very less point contact area, that will keep on increasing the further and further to have more and more point area. Finally, it becomes a surface contact. Even during the joining by other methods like welding or such type of thing, you need to constrain both the lap joint, overlap joint properly, and then you weld. So, what happens when you do, then you have a more contact area, and by that way your contact resistance becomes reduces. So, that is where when you see here, the only the point contacts are there here. This the very small portion in microscope, it has been shown here. So, only very point contacts. So, your current lines got distorted, it has to flow more. So, current density in the particular area becomes very high. So, there would be localized heating, and that localized heating you may not even feel, but it will slowly it will damage the system. And we face this contact resistance in day out basis, because you cannot have infinite length of conductor, and you have to join two cells or multiple cells together, and then there are other wiring harness for sensors, then you have wiring harness for the current flow. So, all those things has to be properly joined, either through nut and bolt arrangement, or I can say mechanical arrangement, or if you wanted to join through welding, the contact becomes very important. So, you have to increase the contact area, so that both this streamline resistance and contact resistance becomes minimum. You do not want any contact resistance there. There is other way also. Sometimes what we do, we try to fill with some gel nanoparticle material, so that my contact area increases and that contact resistance decreases. Now, the next important question which we have already solved a small problem in example, however, we will discuss again the voltage drops in conductors. So, we have two types of conductors there. So, these conductors are important for power delivery, that bus bar, that is very important for power delivery, and then we have another wiring, sensor wiring harness. So, when we talk about sensor wiring harness, that is very essential for monitoring, because if you are not monitoring the things, you cannot take any actions. You will not be able to mitigate any safety aspect. You will not be able to improve the operation of your pack. So, two different types of wiring harness. One is related to the efficient power delivery, like means current flow, and then another one is for the monitoring purpose, like sensor monitoring and control purpose. So, what are the important things you need to check with this? So, in all the cases, in both the cases, you need to find out voltage, current and the temperature. So, that we do monitoring in the power delivery path. So, the harness provides an electrical pathway for power delivery and the measurement of the parameters. Since it is electrical conductor, so there is always a voltage drop, because there would be always a resistance, and because of that there would be always a voltage drop. But when I say voltage drop, what is the acceptable limit of voltage drop? That becomes important. Now, why the voltage drop happens? It is because of resistance, and resistance is related to directly proportional to the length and inversely proportional to the cross sectional area. So, now we have a multiple cells in the battery pack in series and parallel combination, and your BMS is monitoring, and BMS how it is monitoring? It is monitoring by wiring harness. So, there would be some cells very far away and some cells very near away, very near. So, you need to monitor the last cell also, and then you need to monitor the first cells also. For first cells, your wiring length would be very small. However, for the last cell, I consider the last cell is at the farthest away, your wiring length would be quite big, especially when we talk about the big packs. This becomes a problem. And since it is a conductor, so there would be a voltage drop. So, this length and this length is small, this length is at least 6 to 7 times of this length. So, there could be more voltage drop here and the less voltage drop here, because the resistance is proportional to the length. Consider the same cross section area of the wire here. So, the sensing of this and the sensing of this would not be the same. There would be slight differences. How can we mitigate that thing? So, by system calibration, and that can be done in the both way, at the software level or firmware level. We provide a multiplier depending upon the length or the gain factor. And the second one is, let us provide the same length, rapid for the smaller distance, and for the lengthier just let it straight. Now, I am going to put questions here, and then we will see what happens in the conductor, and that means power delivery part and the sensing part. So, generally the wire gauge for the sensing we use 20 AWG, around 0.8 mm square. The length is 300 meters, 300 mm. The resistivity of copper is given. So, the wire resistance is 0.01. So, resistance is quite high. But if you see in the sensing part, the current is very small in milliampere or microampere. So, the measurement current, when I see the 20 milliampere. So, if this resistance would have been there in the current carrying path, where we have to find hundreds of ampere, then it would have been a disaster. But since here in measurement path, the current is very small, very small, in milliampere to microampere it goes. So, my voltage drop is around 0.0002 volt. Now take a conductor carrying path, bus bar. So, we have 14 ampere going, so total 28 ampere going and 28 ampere coming down here. The cross sectional area is 0.2 into 8 mm, length is 16 mm, current 14 ampere, that is what I have taken a single cell. Now, the bus bar resistance is, you see here, the wire resistance is 0.0 ohm, 0.01 ohm here. Here my bus bar resistance is 0.00068 ohm. However, my current is here 20 milliampere, my current is here 14 ampere. Now, voltage drop across this conductor is 0.01 volt, 0.1 volt drop in the current or between cell to cell would reduce, means will give you error in SOC calculation by approximately 8 to 10% at the higher voltage level on 4.1, 4.2 voltage level. 0.01 volt will give you error of 1%, which is acceptable. But if this resistance would have been high enough like this, and that can happen because of the several reasons, contact resistance, or you have not designed the bus bar properly. So, your SOC calculation or SOC estimation or the actual SOC would be drastically different if you have not designed it properly, if you have not considered what could be the voltage drop. Okay? So, 50 times to that voltage drop in harness, and why it is happening? It is because of the very less current here, it is a very high current here, even though my resistance is much smaller than the wiring harness resistance. And why that is happening? Because of the cross sectional area. Now, the current equalization, that is another aspect what we were talking from the start of the class. It is impossible, or I do not say exactly impossible, it is very difficult to carry the huge current. So, there is especially in electronics, even in the power flow path, because when you are, it is again Joule heating, I square R, that always heating comes in that level. If your I is going high and high, your I square would be square times of the current, the heating, and that becomes huge. So, the one of the way to reduce the I square losses is to provide multiple paths. So, you reduce the current. Now, if I have to take out 100 ampere current, it is easy for me to go for 4 parallel paths of 25 ampere each, or 8 parallel paths of 12.5 ampere each, or 10 parallel paths of 10 ampere current flow in each of the path. When that happens, you need to ensure that each of the paths should have the same resistance. Otherwise, if there is slight change in the resistance of any of the path, you will end up more current flowing through that, which you have not considered during the design phase. So, that path will fail. As soon as that path fails, now there is extra current on all other paths. So, one by one, eventually every path will fail. As soon as we are putting the parallel paths, it is impossible to have the same length, or it is very difficult to have always the same length. But we have parameters length and cross sectional area. So, resistance is proportional to length by, it is a diagonally proportional to the length and inversely proportional to the cross sectional area. So, if I am increasing the length, if my length of the path is increasing, what I have to do? I have to also increase the cross sectional area, and the cross sectional area has again 2 factors. One is the width, another one is thickness. So, I can play both of that, and as soon as I play both of that, I can ensure my resistance in all the paths are equal. Now, if you see this picture here, I have 4 paths, I1, I2, I3, I4. Now, 1 and 4, if you see 1 and the 4 has high resistance because of the length. If I keep cross sectional area same, so in that case path 1 and 4 will have high resistance, and because of the resistance, high resistance here, the lower current will flow from path 1 and 4. Path 2 and 3, since length is low, if I keep cross sectional area same, so we will have lower resistance and the higher current will flow. However, I2 and I3 will have the same current because the resistance is same in both the path. I1 and I4 will have the same current because the resistance in both the paths are same because of the length, if cross sectional area is same. But I1 and I2 is not same, I2 and I3 is same, I1 and I4 is same here, but I1 and I2 is not same because of the different length. So, since length is increasing, so I can change the cross sectional area, that is in our hand during the design phase. And how do we do that? So, the path resistance R is nothing but rho L by A, that means R is proportional to L by A. So, if I have to make R1, R2, R3, R4 same, so R1 equal to R2 equal to R3 equal to R4 is nothing but L1 by A1 equal to L2 by A2 equal to L3 by A3 and equal to L4 by A4, and that is supposed to be a constant. Now, when I say cross section, again I can fix one thing, I can vary other thing, width and thickness, I have two parameters. So, depending upon the situation, depending upon the design constraints, packaging constraints, I can think what should I increase, but I can always make the resistance in all the paths equal, and that is a must, otherwise one by one my everything will fail. So, example on that, a bus bar carrying current at 10.5 ampere across the voltage drop of 3.5 volt is split into two paths of unequal width and the thickness T. If the smaller path is of length 40 mm, while the larger path length is 80 mm, find the width of each path assuming current to be equal in both. What is the magnitude of current flowing through each path? That also we need to find. So, solution simple, from V equal to IR, from that we have resistance is 1 by 3 ohm. Now, resistance of each path R1 and R2 we need to find out, since B1 equal to B2 and I1 equal to I2. So, R1 equal to R2. So, one again both are in parallel. So, that formula has been applied. Solving this two, you will find R1 equal to R2 equal to 2, that is nothing but 2R, that is a 2 by 3 ohm. Then you need to find the R you know, now you know what is the R, and from that you can find out this rho L1 by A1 equal to rho L2 by A2. So, L1 you know, L2 you know, T1 equal to T2, that also you know because the thickness is same T. So, you can find out W1 and W2. So, L1 W1 equal to 2 by 3. So, 48. So, W1 is 61. W1 is the width of, once you know W1 you will find out the W2 also. So, since you have found out everything, so I1 is equal to I2. So, that becomes 5.25 ampere because we have a total 10.5 ampere, and this you can cross verify by putting this value in all the things that you are getting same or not. The next important thing what I was talking during the contact resistance time is joining techniques. So, there are different types of joining method, mechanical joining, then you can also weld, and the welding we have a different types of welding, that laser welding, ultrasonic welding and spot welding, and all those three have its own merits and demerits. Generally, laser welding is good because it does not heat nearby surfaces. It is a fast, reliable, much better welding strength. However, the equipments are quite costly. For a small scale, you do not want to have. Ultrasonic weldings are good for very thin materials, very thin. If your current requirement is very small, in such cases ultrasonic welding can help. It is very good for again the plastic enclosure welding. In such cases, when you have to maintain the IP ratings and other things, the ultrasonic welding works well. Then third one comes spot welding. When I say spot welding, it can be done using the laser welding also, but here what we say is resistance welding. It is basically resistance welding. The weld is formed by pressure and the current flowing through that. So, by the interfacial resistance through that the weld point is formed. This is very good for the small scale and where we have the very small current carrying path, when we have a small current carrying requirement. In such cases, this spot welding works very well. Comparatively, the equipments and setup is very cheap and the very less time consuming. The advantage of resistance or projection welding, it is very fast, low cost, good quality. I do not say great quality, good quality. Good quality control you have. It can be easily automated. It is difficult to weld very high conductive, which you wanted to have the very low resistance, but it is difficult to weld using very high conductive material through resistance welding. Another difficulty is very large joint is difficult to use this thing. You can do, but then again you have to have a very large setup for such things. Laser welding, high speed, very less thermal input is there. So, almost non-contact process, very high degree of automation is possible. Again, its cost is quite high and the operation and maintenance cost is also very high and not great for the highly reflective materials. So, what you see here, resistance welding works on mostly pressure and the interfacial resistance, and here you can simply put the laser beam which can weld out. How do you test these weld joints? So, there are different tests, peel test and the chisel test. So, you pull out the weld at some particular force, and if it has come out, then you know what the welding strength in during the peel test. Force is applied in such a way that it is always perpendicular to the original orientation of the weld. It can be performed manually by fixing some strain gauge, so that what force you are taking putting it there, and can also be done automated by using a good lab equipment. Now, in chisel test, you put a chisel and the hammer it, or you apply the force over that one, and if it is coming out, you would be able to know at what force that weld is coming out. So, I will summarize electrical design, what we have discussed. Electrical design of the battery pack, you have various factor of cells depending upon the cost, availability, performance. We select a type of cell, then using MP-NS theory, M parallel, N series, parallel first, series second, we derive capacity, voltage and current requirement. We also work out during that time what could be the space constraints, which anyway we will talk in the next class in mechanical design of the battery pack. We divide into the whole requirement, we divide into the modules, and we prepare one module by combination of cells in parallel and the series combination. Now, then we assemble the modules, then mostly by series combination we make the battery pack. The next important thing in the electrical design is the design of a bus bar. Should have a good current density carrying capacity. It should be sufficiently ventilated, so that temperature would never cross the safe limit of the material or design criteria. It should be easily manufacturable and we should be able to assemble it easily. Wherever you are reducing the cost in manufacturing and assembly, it is finally you are reducing the cost of the battery pack. Cost effective material solution, yes, silver and golds are highly conductive, but we cannot utilize because of its cost. What could be the best material? Copper, aluminum, alloys, various alloys. What we have to worry about mostly is how to minimize the resistance or resistivity of the material. The next thing what we have discussed about the current carrying path, we should be able to estimate, calculate and measure the voltage drop across the current carrying paths, and that should be minimum. So, we have to design in such a way that the voltage drop across the current carrying path should be minimum, should have sufficient electrical insulation to mitigate any safety concerning issues and also EMC EMI noise. It should be mechanically safe and rigid, so that even in the adverse condition it should not worn out or break out. If we have to divide the current into multiple paths, all the paths would have the equal resistance. There are multiple methods of bus bar joining, but should have good mechanical strength, minimal contact resistance. Any type of resistance we always try to minimize. Different types of joining methods: laser, ultrasonic, spot welding. There is another method also, mechanical joints, various protections, fuses, thermal, electrical, etc. Design should take care of EMC EMI noise suppression, and so the varying environmental conditions should not impact the current carrying capacity or sensing capacity of the wire harness. There are several other things like contactors, relays and all those things which we will talk about during the BMS design. So, in the next class we will start with the mechanical design of the battery pack, fundamentals of mechanical design of a battery pack. Okay? Thank you.